What's up guys, welcome back to Simple Science. Today we're going to be going over everything in AP Chem Unit 2. Okay, so this unit is all about the different types of chemical bonds, so we're going to start by going over the different types of chemical bonds.
On the periodic table, elements can be classified into metals, nonmetals, and metalloids. And metals can be found from groups 1 to 3, with some exceptions, as well as the giant block of transition metals in the center. Nonmetals are found in the top part of the right-hand side of the periodic table, and metalloids form a bit of a division between the two, kind of like the staircase over here.
The first type of bond that I want to go over is ionic bonds.
Ionic bonds are formed between a metal and a nonmetal, or sometimes a polyatomic ion. In an ionic bond, a metal typically transfers some electrons to the nonmetal.
But why is that? Turns out it all has something to do with valence electrons. Each group on the periodic table has a specific number of valence electrons, and every atom wants to either get 8 valence electrons in its outermost shell or none at all. Let's look at the valence electrons that the metals have. On the periodic table, excluding the transition metals, metals generally have anywhere from 1 to 3 valence electrons, depending on what group they're in. Because they have so few valence electrons, they'll typically give away their few valence electrons to get a stable electron configuration. This means that they'll form positive ions or cations in ionic compounds since they lose negatively charged electrons. For example, magnesium has 2 valence electrons since it's in group 2. In ionic compounds, magnesium will give away those 2 electrons to a nonmetal, becoming the magnesium 2+ ion. Now let's look at nonmetals. With the exception of hydrogen and maybe boron, nonmetals tend to have 4 or more valence electrons. This means that in ionic compounds, they'll take electrons away from the metals in order to gain 8 valence electrons in their outermost shell. How many electrons they'll get depends on the amount of electrons they need to complete their outer shell, giving the outer shell 8 electrons. For example, phosphorus has 5 valence electrons, and it needs 3 more to get an octet, which is just another word for 8 valence electrons. So, in ionic compounds, phosphorus gains 3 electrons, becoming the phosphorus 3- ion. Elements in group 16 will gain 2 electrons, and elements in group 17 will gain 1 electron. So, nonmetals typically form anions, which are negatively charged ions. Nonmetals in group 14 can either gain or lose 4 electrons, since they have 4 valence electrons, and can either have 8 in the outermost shell or none at all. So now we're going to talk about naming ionic compounds and finding their formulas. On the AP test, you may be given the name of an ionic compound and asked to find its formula, or vice versa.
To find this formula, first you need to find the charges of the metal ion and the nonmetal ion in the compound. Then, you need to make those charges the subscript of the other ion.
Let me explain how that works with an example. Let's say that calcium and nitrogen are going to form an ionic compound. Calcium, the metal, has 2 valence electrons, and nitrogen, the nonmetal, has 5 valence electrons. Calcium will lose 2 electrons to become the calcium 2+ ion, and nitrogen will gain 3 electrons to become the nitrogen 3- ion. But if calcium gives its 2 electrons to nitrogen, that's still not enough. Nitrogen would need 1 more electron in order to become stable. So, to balance the transfer of electrons, we take the charges of calcium and nitrogen and make them the subscripts of the other atom. So, the ionic compound will have The ionic compound will have 3 calciums and 2 nitrogens. If there are 3 calcium 2+ ions, there will be 6 valence electrons for calcium to give to nitrogen. And if there are 2 nitrogens, the nitrogens in total will need 6 valence electrons. This works out. The calciums will transfer their 6 electrons to nitrogens, and both of the atoms will become stable. This is why we turn the charges of each ion into the subscripts of the other ion in the compound. If, however, the ions have the same net charge, like a +2 ion bonding with a 2- ion, the subscripts will stay 1-to-1, since one ion can transfer electrons to one other ion to become stable. For example, magnesium has 2 valence electrons, so it donates 2 electrons and becomes a 2+ ion in an ionic compound. Oxygen has 6 valence electrons, so it receives 2 electrons and becomes a 2- ion in an ionic compound. In magnesium oxide, a single magnesium will donate 2 electrons to a single oxygen ion, which needs those 2 electrons, and both atoms will become stable. So you don't need to turn their charges into the other ion subscripts. The formula will just be MgO.
Now, I know you can find the amount of valence electrons in atoms from groups 1, 2, and from groups 13 to 18, and use those valence electrons to find their charges in ionic compounds, but what about transition metals? Well, if you remember from Unit 1, transition metals have d orbitals in their electron configuration, which kind of makes getting 8 or no electrons in their valence shell a bit complicated. So, most transition metals have multiple charges they could make in an ionic compound, with the exception of the following. Silver forms +1 ions, and zinc and cadmium both form 2+ ions. You need to memorize these charges for the AP test. In addition, you also need to memorize a list of polyatomic ions and their charges. I'll link a set of flashcards to memorize them in the description. Polyatomic ions are ions that are made out of multiple different atoms. For example, the nitrate ion's formula is NO3, and it has a total charge of -1, meaning it gains 1 electron in ionic compounds.
Now, let's talk about naming ionic compounds.
In an ionic compound, put the name of the metal or positive ion first, and then put the name of the nonmetal or negative ion last. If there is a nonmetal in the ionic compound, you replace its suffix with IDE.
In the compound NaCl, which has sodium and chlorine, you would put sodium's name first and then put chlorine's name. Since chlorine is a nonmetal, you would replace the suffix INE in chlorine with IDE. So NaCl will have the name sodium chloride.
If you have a negative polyatomic ion instead of a nonmetal, you keep the name of the ion without changing anything.
For example, if you had an ionic compound with magnesium and phosphate, which has a magnesium 2+ ion and a PO4- ion, you would put the metal's name first. In this case, it's magnesium. Then you would put the negative ion's name last, writing out phosphate. Since phosphate is a polyatomic ion and not a nonmetal, you would leave the suffix as is. So the entire compound's name would be magnesium phosphate. Now we're going to talk about the different properties of ionic compounds, starting with how they're structured.
Ionic compounds are arranged in lattice structures which alternate the positive and negative ions in rows of a lattice, which is another name for a block of an ionic compound. This happens because positive and negatively charged particles are attracted to each other, and they're repelled from particles that have the same charge as them. So, with charged ions in an ionic compound, the positive ions will be attracted to the negative anions, and vice versa, creating a repeated pattern that separates particles with the same charge and pulls together particles with a different charge. Because ions have a completely positive and a completely negative charge, the attractions between them are strong, and the ionic bonds in a lattice structure require a lot of energy to break. Because of this, ionic compounds have a high melting point. And also, because a lattice structure is so strongly held together, ionic compounds are brittle, meaning they can't be bent or stretched like metals can. In addition, ionic compounds are highly soluble in water, where they split into their separate positive and negative ions. Because they split into charged particles in water, ionic compounds conduct electricity when dissolved in water, since electricity is conducted through free-moving charged particles. However, in their solid form, the ions in ionic compounds can't move too much, due to their strong lattice structure holding them together. This makes them poor conductors in solid form.
Speaking of lattice structures, it's now time to go over comparing the different lattice energies for different ionic compounds.
Lattice energy describes how strong the bonds are between ions in an ionic compound. Specifically, it describes how much energy it takes to break attractions between a mole of an ionic compound, in order to convert it into a gaseous state. Ions with a high magnitude of charge will have a high lattice energy. For example, when comparing the lattice energy of sodium fluoride and sodium oxide would have a greater lattice energy, since the oxygen 2- ion has a greater magnitude of charge than the F- ion.
Believe it or not, distance is also a factor in comparing lattice energy.
Compounds with ions with a larger atomic radius, due to a greater number of shells, will have a lower lattice energy than ions with a smaller ionic radius. This is because larger atomic radius decreases attractive forces between different ions.
For example, let's compare the lattice energies of sodium fluoride and lithium fluoride. Lithium has 1 energy level, while sodium has 2 energy levels. Because of this, sodium has a larger ionic radius than the lithium ion. So, sodium fluoride has a lower lattice energy than lithium fluoride. But what if you're comparing two compounds that have both different magnitudes of charge and different atomic radiuses? Wait, is it radiuses? Or is it radii?
In that case, the ionic compound with a greater magnitude of charge would have the highest lattice energy, since charge is a more important factor in lattice energy than distance. You can remember this with the saying, charge trumps distance.
Let's look at an example. This problem gives us the lattice energy for two different ionic compounds, X and Y. One of the ionic compounds is LiCl, and another one of the ionic compounds is MgCl2. Compound X's lattice energy is negative 2,574 kilojoules per mole, with the negative just indicating a release of energy once the compound is formed. Compound Y's lattice energy is negative 834 kilojoules per mole. The problem asks us which compound is compound X. Well, compound X has a greater magnitude of lattice energy. So we need to find the compound with the strongest lattice energy, and that's going to be compound X. Both LiCl and MgCl2 have a chloride ion, so we're going to be comparing the properties of the lithium ion and the magnesium ion. Lithium has 1 energy level and magnesium has 2 energy levels, so magnesium has the largest radius. Because of this, you would think that magnesium chloride has a lower lattice energy. However, the lithium ion has a +1 charge and the magnesium ion has a +2 charge. In this situation, we care more about charge than distance when comparing the lattice energies. So, because MgCl2 has a greater magnitude of charge, it has a greater lattice energy, making MgCl2 compound X. Let's move on to our next type of bonds, which are covalent bonds. In an ionic bond, the metal usually transfers electrons to a nonmetal, creating an attraction between the two particles.
However, in a covalent molecule, nonmetal atoms share electrons to form covalent bonds, each of which is made up of 2 electrons. A single bond has 2 shared electrons, a double bond has 4 shared electrons, and a triple bond has 6. Covalent compounds usually have low boiling and melting points, and they don't really conduct electricity at all.
Covalent bonds can either be polar or nonpolar.
Polarity refers to how 2 atoms share electrons in a covalent bond. If one atom pulls the electrons in a covalent bond towards itself, the bond is polar. However, if both atoms share electrons equally, the bond is nonpolar. You can determine if a bond is polar or nonpolar by looking at the 2 atoms' electronegativity, which is how strongly an atom pulls electrons towards itself. Atoms with a high difference in electronegativity have a relatively polar bond, and atoms with a low difference in electronegativity have a relatively nonpolar bond.
But how do you determine electronegativity?
We talked about Coulombic attraction in Unit 1. Atoms with a high Coulombic attraction had a higher effective nuclear charge and a low number of energy shells. It turns out atoms with higher Coulombic attraction also have high electronegativity, since they can attract electrons towards themselves. So, atoms at the top right have a high electronegativity, and atoms at the bottom left of the table have a low electronegativity. You can measure the difference in electronegativity by counting the number of jumps between atoms on the periodic table. Elements with a lot of jumps between them will have a large electronegativity difference, giving them a more polar bond. Elements with less jumps between them will probably have a low electronegativity difference, giving them a less polar bond.
For example, this question asks us which of these bonds is more polar, a bond between oxygen and sulfur, or a bond between oxygen and bromine. The question asks us about polarity, so we need to look at the difference in electronegativity between the two atoms. The atoms with the largest electronegativity difference will have the most polar bond. On the periodic table, oxygen is right above sulfur, making them only one jump away from each other. However, bromine is 2 spaces down and 1 space to the right of oxygen, making it 3 jumps away from oxygen. This means that oxygen and bromine have a larger electronegativity difference than oxygen and sulfur, making oxygen and bromine's bond more polar. In this bond, since oxygen is more electronegative than bromine, oxygen would pull the electrons towards itself, making it partially negative and making bromine partially positive.
Alright, you guys are not gonna believe what happened yesterday.
Alright, man, what happened?
So yesterday, I took my electrons to the pool.
Okay.
And all of a sudden, I got one of them running up to me, going like, "Oh my gosh, Mom, why is the water so warm?"
Oh boy.
So I gotta walk over to the pool, and all of a sudden, as soon as I step in, I notice the water is like weirdly warm. Just kind of weird, because it's usually like freaking freezing.
Oh, that's just disgusting.
Oh, don't worry. It gets much worse. So I start to feel the water getting like really, really warm, like basically hot at this point. And I look down at my electron, and she's looking up at me, and she's smiling. And the water all around her is just like bright freaking yellow, like lemon yellow. And then she looks up at me, and then she says, "Mom, it's getting warmer."
Oh, that's just freaking disgusting. But, you know, you gotta love your electrons. I mean, absolutely nothing beats hearing them say their first words.
Oh man, I remember those days. It was like, when they said their first words, it was like the sweetest thing I've ever heard in my whole life.
Hey, Carbon.
Yeah, man, what's up?
Hey, where are your electrons, man? I haven't heard you talk about them in so long.
Oh, that. So y'all remember my ex-wife, Florine, right? We had that big, messy divorce, everything. So she got the electrons in the divorce, and I can only really see them about every other weekend. Ooh, that sucks, man. I swear to all the courts, they always give it to the most electronegative atom. It's really hard, man. I mean, they're my electrons too, but nowadays, I don't even really feel like a parent, you know?
Yeah, man, it's pretty hard being in a polar bond. I mean, if my wife was more electronegative than me, I wouldn't see my electrons, like, at all.
What are you even talking about, man? You're like one of the most electronegative atoms out there. Okay, he might be electronegative, but he can
Hold on, man. It's my ex-wife on the phone.
Hey, what's up, man?
What do you mean you talked to your lawyer? The divorce is over, Flo. 1 weekend? Every other month? Are you crazy? They're my kids too. They're my electrons too, bro. Alright. I bet you don't even know their birthdays. Okay, what are their birthdays? Tell me. See, I knew. The second you pulled out those papers, I knew. You were just out for those electron support payments, bro. You don't even really care about them.
Another skill that you're going to need to learn is how to draw Lewis dot structures.
These structures show how different atoms are arranged in a covalent molecule, including which atoms are bonded to which, and how many lone pairs of electrons are on an atom.
But before we can go over drawing Lewis structures, we first need to go over some principles of covalent bonds.
Most atoms and covalent molecules need to get an octet of 8 valence electrons, with some exceptions that we'll go over later. This means that when drawing the Lewis dot structures, we'll need to make sure each atom gets 8 electrons by being bonded to other atoms or through having lone pairs of electrons on them.
In addition, all of each atom's valence electrons need to be used when drawing the Lewis dot structures. So, we first count the total number of valence electrons in all the atoms before drawing a Lewis dot structure.
There are a lot of methods to drawing a Lewis structure, but I usually like to do this. First, find the number of valence electrons that each atom has, and then add them all up. Then, put the element with only one atom in the compound in the center, and draw the other elements surrounding it. Connect those other atoms to the atom in the center.
After doing the basic stuff, your goal is going to be to give each atom 8 valence electrons, whether through bonds or lone pairs, without exceeding the total number of valence electrons in the whole molecule.
I like to start by finding the number of lone pairs on the central atom, with the lone pair being 2 electrons that aren't in bonds. You can do this using the following formula. The number of valence electrons minus 8 times the number of atoms bonded to the central atom divided by 2.
Then you can start adding lone pairs to the non-central atoms to give them an octet. Or you can convert some of the lone pairs into double or triple bonds if you run out of valence electrons.
Let's do a quick example. Here we're going to be drawing the Lewis structure for sulfur dioxide, aka SO2. First, we count all the valence electrons in this molecule. Sulfur and oxygen are both in group 16, so they each have 6 valence electrons. There's 1 sulfur and 2 oxygen. Each one of those atoms has 6 valence electrons. So we take 6 times 3, which is the number of atoms, to give us 18 total valence electrons that we can use to draw the structure. Next, we place the single element, sulfur, in the middle, with 2 oxygens surrounding it. The oxygens will each form a bond with sulfur, so we draw a line representing a bond here and here. Each bond represents 2 shared valence electrons, so we've used 4 out of the total 18 valence electrons. To find the number of lone pairs, we use the formula that goes like number of valence electrons minus 8 times the number of atoms bonded to the central atom, all of that divided by 2. The total number of valence electrons is 18, and the number of atoms bonded to sulfur, the central atom, is 2. 18 minus 2 times 8 is 16, that's not math. 18 minus 2 times 8 is 2. 2 divided by 2 is 1, so there's 1 lone pair on sulfur. We divide 2 by 2 to get 1 lone pair on the central atom. Now we focus on giving each atom 8 total valence electrons. Sulfur already has 6 due to its lone pair and 2 bonds, so it only needs 2 more valence electrons. Those electrons can't be in the form of a lone pair, since our formula told us that there can't be more than 1 lone pair on the central atom. So we add 2 electrons in the form of a double bond to oxygen. Now sulfur has 8 valence electrons. Now this oxygen over here has 4 valence electrons because of this double bond over here. So we add 4 more in the form of lone pairs. This other oxygen only has 2 because of this 1 single bond with sulfur. So we add 3 lone pairs. Now we check how many valence electrons we have versus how many we used. If you count the total number of valence electrons here, including 2 for each lone pair and 2 for each bond, you get 18 electrons total. And that matches the total number of valence electrons we needed to use, so we're done.
If the amount of valence electrons used is greater than the number needed, you likely need to convert some lone pairs into double bonds by erasing a lone pair from 2 atoms and drawing a bond between them.
There are some exceptions to the octet rule, which says that each atom needs 8 valence electrons to be stable. Hydrogen only needs 2 electrons, and both beryllium and boron often have less than 8 electrons, but not always.
In addition, all the atoms in and past the 3rd energy level can form more than 4 bonds with different atoms, since they have access to a d sublevel that can hold extra electrons.
Now that you know about Lewis structure, it's time to learn about electron and molecular geometry.
Electron geometry is the amount of electron regions around a central atom in a covalent molecule.
Electron regions is just another way of saying the amount of atoms bonded to the central atom and the amount of lone pairs on the central atom.
A molecule with 2 electron regions is called linear, and the angle between the bonds is 180 degrees. A molecule with 3 electron regions is trigonal-planar, with a bond angle of 120 degrees. A molecule with 4 electron regions is tetrahedral, with a bond angle of 109.5 degrees. A molecule with 5 electron regions is trigonal bipyramidal, with a 120-degree bond angle between these atoms on the midline, and a 90-degree bond angle between these guys over here. Finally, a molecule with 6 electron regions is called octahedral. All of its bond angles are 90 degrees.
Molecular geometry is a molecule's electron geometry that specifies how many lone pairs the central atom has. So, while two atoms could have the same electron geometry, meaning they have the same number of electron regions, they could have different molecular geometries based on how many lone pairs the atom has.
This probably sounds really confusing, so let's look at an example. These are the Lewis dot diagrams for water and carbon tetrachloride, aka CCl4. Let's look at their electron geometry. CCl4 has 4 bonds and no lone pairs on the central atom, so its electron geometry is tetrahedral. Water has 2 lone pairs and 2 bonded atoms, so its electron geometry is also tetrahedral. However, while CCl4 has no lone pairs, water has 2. This gives water a different molecular geometry than CCl4. Its molecular geometry is bent, which is the name for an atom which has 2 bonded atoms and 2 lone pairs on the central atom. Meanwhile, CCl4's molecular geometry is tetrahedral, the same as its electron geometry. I'll leave a link to a molecular geometry chart in the description, since I don't have time to go over each and every shape.
If a molecule has no lone pairs, you assume its bond angles are the same as its electron geometry. If a molecule has 1 or more lone pairs on the central atom, you assume its bond angles are slightly less than its electron geometries. This is because lone pairs of electrons on the central atom tend to repel the bonds attached to the central atom, pushing them away from the lone pairs and slightly closer towards each other.
Let's look at the bond angles in NH3 as an example. NH3 has 4 regions of electron density from 1 lone pair and 3 bonds on the central atom. This means its electron geometry is tetrahedral, and tetrahedral atoms generally have tetrahedral molecules generally have a bond angle of 109.5 degrees. However, NH3's molecular geometry is trigonal pyramidal because it has 1 lone pair. This 1 lone pair will repel the bonds away from itself, pulling the bonds closer together and decreasing their bond angle. So we can say that NH3's bond angle is slightly less than 109.5 degrees. Now that we've gone over how to draw a Lewis dot structure, it's time to talk about resonance. Let's say that you've drawn a Lewis dot structure for CO3. There's a double bond between this oxygen and this carbon atom. However, another way you could draw this molecule is by putting the double bond next to this oxygen. You could also draw the double bond next to this oxygen over here. So you're probably wondering which of these structures is correct. Turns out that these are resonance structures, which are different forms of the same molecule. These different structures are drawn by placing a double/triple bond or a lone pair of electrons on different atoms. It turns out that all of these resonance structures exist at the same time, with the double bond being split up between these 3 oxygens. Alright, hold up a second. And we've got our first Steve question of the day. What is it, Steve? If the double bond is split up because of the resonance structure, is even really a double bond? Well, not exactly. Because each double bond is split up between these oxygens, each bond in CO3 is somewhere between a single bond and a double bond, making it some sort of kind of a fractional bond.
We can find out the exact bond order of these bonds by dividing the total number of bonds in the atom by the number of areas the bonds could be in. Bond order is just another way to describe the amount of chemical bonds between atoms. Single bonds have a bond order of 1, double bonds have a bond order of 2, and triple bonds have a bond order of 3. Resonance structures like CO3 usually have a bond order in between these numbers.
Let's try to find the bond order for CO3. First, we need to count the total number of bonds in the atom. There are 1, 2, 3, 4 bonds in the atom, since double bonds are made up of 2 bonds. Now we need to count the number of areas that the bonds could be in. The bonds could be here, here, and here, so there are 3 areas. Dividing 4 by 3, we get a bond order of 4/3. So every bond in CO3 has a bond order of 4/3, instead of there being 1 double bond and 2 single bonds. Let's look at another example. This problem gives us the Lewis structure for O3, aka ozone, and asks, what is the bond order of this molecule? Before looking at the bond order, we first need to figure out if O3 has any resonance structures. Well, I see a double bond over here, and because there's another oxygen, we can also assume that we could draw the diagram like this, with the double bond on the other oxygen. This means that there are two resonance structures for this molecule. Now that we know there are resonance structures, we can assume that the double bond is split up between these two oxygens, so the bond order is going to be a type of fraction. To find the exact bond order, we first find the total number of bonds in the molecule. There are 1, 2, 3 bonds in O3. Then we count how many areas the bonds could be in. There are 2 areas you could place this double bond. 3 divided by 2 is 3/2, so the bond order is 3/2. As it turns out, not all resonance structures are created equal. We can use a concept called formal charge to figure out which resonance structure is the best if we have some different choices.
Formal charge is the charge of an individual atom in a molecule.
If you're trying to pick the most stable resonance structure for a molecule, pick the resonance structure with the most formal charges as close to 0 as possible. This indicates that the atoms in a particular molecule are pretty neutrally charged, making the structure generally more stable.
And now is the time where I stop blabbering and tell you how to actually find the formal charge for an atom.
For an atom in a particular molecule, you can calculate the formal charge by subtracting the number of unpaired electrons and bonds connected to the atom from the atom's number of valence electrons.
For example, this problem asks us to find the most stable resonance structure for SCN, aka thiocyanate. And we've got 2 resonance structures over here. In this structure, carbon is in the center and sulfur and nitrogen are bonded to it. Let's find the formal charge for each of these atoms, starting with nitrogen. We find the formal charge by subtracting the number of unbonded electrons and the number of bonds the atom has from the atom's total number of valence electrons. Nitrogen has 5 valence electrons, and in the structure, there are 4 unbonded electrons on it, since each lone pair has 2 electrons. So we subtract 5 minus 4. Next, there are 2 bonds connected to nitrogen, since there's a double bond. So we subtract 2 from that. 5 minus 4 minus 2 equals -1, so nitrogen's formal charge is -1. Now let's do carbon. Carbon has 4 valence electrons. We can see there are 4 bonds connected to carbon, so we do 4 minus 4. There are no unbonded electrons on carbon, so carbon's formal charge is 0. Finally, let's do sulfur's formal charge. Sulfur has 6 valence electrons. There are 2 bonds connected to sulfur, so we subtract 2 from 6. There are 4 unbonded electrons on sulfur, so we subtract 4 from this. 6 minus 4 minus 2 equals 0, so sulfur's formal charge is 0. This structure is looking pretty good so far. 2 of the formal charges are 0, and -1 is pretty darn close to 0. Now, let's look at the other resonance structure. This one has nitrogen in the center, and carbon and sulfur bonded to it. Let's start with finding the formal charge for carbon. Like we said before, carbon has 4 valence electrons. In this one, there are 2 bonds attached to carbon, so we subtract 4 from 2. And there are 4 unbonded electrons on carbon, so we subtract 4 as well. 4 minus 2 minus 4 gives us -2, so carbon's formal charge is -2. Now let's look at nitrogen. Nitrogen has 5 valence electrons. And there are 4 bonds attached to nitrogen, so we subtract 4 from 5. There are no unbonded electrons on nitrogen, so we stop there. 5 minus 4 equals 1, so nitrogen's formal charge is +1. For sulfur, we know that it has 6 valence electrons, and there are 2 bonds attached to sulfur, so we subtract 2 from 6. There are 4 unbonded electrons on sulfur, so we subtract 4 from that also. 6 minus 2 minus 4 equals 0, so sulfur's formal charge is 0. Comparing the 2 resonance structure, this first structure has the most charges that are close to 0, whereas the second resonance structure has a -2 on carbon. That doesn't look too good. So The first resonance structure is the most stable. But what if you have to choose between resonance structures that have the exact same formal charges, just arranged on different atoms? How would you know which resonance structure to pick?
In that case, the structure that places the greatest formal charge on the most electronegative atom is the most stable.
These are two resonance structures for the cyanate anion, which is NCO with a -1 charge. The problem wants us to pick the most stable resonance structure. The formal charge for this nitrogen is 0. 5 valence electrons minus 2 unbonded electrons minus 3 bonds. The formal charge for this carbon is 0. 4 valence electrons minus 4 bonds. The formal charge for this oxygen is -1. 6 valence electrons minus 6 unbonded electrons and minus 1 bond. For this resonance structure, the formal charge for N is -1. 5 valence electrons minus 4 unbonded electrons and 2 bonds. The formal charge for this carbon is 0. 4 valence electrons minus 4 bonds. And finally, the formal charge for this oxygen is 0. 6 valence electrons minus 4 unbonded electrons and 2 bonds. So, as you can see, the formal charges for these resonance structures are basically the same. 2 atoms with a charge of 0 and 1 atom with a charge of -1. So, which resonance structure is correct? In this first structure, the -1 charge is placed on oxygen, and in the second structure, the -1 charge is placed on nitrogen. Like we said before, the structure that places the formal charge on the most electronegative atom is the most stable in this case. Oxygen is the more electronegative atom compared to nitrogen, since electronegativity increases as you go to the top right of the periodic table. So, the first structure is correct since it places the largest formal charge on oxygen. Now we're going to go over sigma and pi bonds. Wait, did you just say sigma? Sigma and pi bonds are two different types of covalent bonds that can form between atoms.
Sigma bonds are strong covalent bonds that form when 2 atoms' electron orbitals overlap directly, forming a bond. Pi bonds are weaker covalent bonds that form when 2 atoms' orbitals overlap sideways. Single bonds have 1 sigma bond. Double bonds have 1 sigma bond and 1 pi bond. And triple bonds have 1 sigma bond and 2 pi bonds.
Some questions will ask you to find the number of sigma and pi bonds in a molecule. In this problem, we have a molecule, and the problem asks us how many sigma and pi bonds there are. First, let's count the number of single bonds in the molecule. There are 1, 2, 3, 4, 5, 6, 7, 8 single bonds in the molecule. Each single bond has 1 sigma bond, so we've just counted 8 sigma bonds. There's 1 double bond in this molecule and 1 triple bond. 1 double bond has 1 sigma and 1 pi bond. So far, we can count 9 sigma bonds and 1 pi bond. Each triple bond has 1 sigma bond and 2 pi bonds. So our final total is 10 sigma bonds and 3 pi bonds. And now it's time to go over bond hybridization.
So we know that atoms keep their electrons and energy levels, but what happens to those energy levels when atoms make covalent bonds? Turns out when making covalent bonds, the central atom will combine the s, p, and sometimes the d orbitals from its outermost energy shell to make one big hybrid orbital. This is called bond hybridization. By making this hybrid subshell, the central atom creates orbitals that each have 1 electron in them. The central atom can then share those electrons with the atoms bonded to it, filling up those orbitals and creating a bond.
There are different types of hybridized orbitals based on how many s, p, or d orbitals are in them. A central atom with sp hybridization, for example, has 1 hybrid orbital made from a single s orbital and a single p orbital. A central atom with sp2 hybridization has a hybrid orbital made from 1 s orbital and 2 p orbitals. If the central atom has an sp3 hybridization, its hybrid orbital is made from 1 s orbital and 3 p orbitals. And finally, if the central atom has sp3d hybridization, the central atom's orbital has one s orbital, 3 p orbitals, and 1 d orbital.
You can determine the type of hybridization the central atom has by looking at the combined number of sigma bonds and lone pairs on the central atom.
A central atom with a combined number of 2 sigma bonds/lone pairs has sp hybridization, and an atom with a combined number of 3 sigma bonds/lone pairs has sp2 hybridization. An atom with a combined number of 4 sigma bonds/lone pairs has sp3 hybridization. An atom with a combined number of 5 sigma bonds and lone pairs has sp3d hybridization, and an atom with a combined number of 6 sigma bonds/lone pairs has sp3d2 hybridization. That was a mouthful. In chemistry, we call the combined number of sigma bonds and lone pairs the atom's steric number. Let's try to find the hybridization for 2 different molecules. This problem asks us to find the hybridization of the central atom for 2 different molecules, SO2 and CO2. In SO2, the central atom is sulfur. Sulfur has 1 lone pair and 2 sigma bonds, so the combined number of sigma bonds and lone pairs is 3, giving it a steric number of 3. Looking back at our chart, we know that this means that SO2 is sp2 hybridized. In CO2, there are 2 double bonds attached to carbon, the central atom. Each double bond has 1 sigma bond and 1 pi bond. But when we're talking about hybridization, we really only care about sigma bonds. Since there are 2 double bonds, there are 2 sigma bonds attached to carbon and no lone pairs. This makes the steric number 2, giving CO2 sp hybridization. And now we're going to move on to our last type of bonding, metallic bonding.
Metallic bonds are usually between 1 or more metals.
With metallic bonds, positive metal ions are usually arranged in rows and different structures, with delocalized electrons floating everywhere in the spaces between the ions. Metals are good conductors of electricity in their solid state because electricity can run through the free-floating electrons.
Because metallic bonds are so strong, metals have a high melting point, since it takes a lot of energy to break metallic bonds and convert solid metals to a liquid state.
Metals are also really malleable, meaning they can be hammered. They're also pretty ductile, meaning they can be stretched out into thin wires.
This is because the free-floating electrons in metallic bonds allow metal ions to slip past each other easily, making them pretty flexible.
Metals can also form alloys, which is when different metal ions are put together to create metallic bonds. Metals can also create alloys with different nonmetals, such as carbon.
For example, when looking at the periodic table for the first time, you might have expected to find steel as an element in the metals section. But unfortunately, steel isn't there. Why is that? It's because steel is an alloy of different metallic elements on the periodic table, specifically iron and carbon.
There's 2 different alloys that we're going to be talking about, interstitial alloys and substitutional alloys.
Interstitial alloys are formed with multiple metals with a big difference in atomic radius.
The smaller metal will try to squeeze in the gaps between the larger metal.
Substitutional alloys are formed with multiple metals with a similar atomic radius.
Instead of squeezing in the gaps, one metal will completely replace another metal's cations in its metallic structure, making an alloy that kinda looks like
a frustrating game of Connect 4.
Interstitial alloys are less malleable than their individual elements, since smaller metals fill in the gaps between larger ones, making the structure more rigid.
Meanwhile, substitutional alloys are more malleable than their individual elements. We've been talking about chemical bonds for just about this entire video. That brings up the question, how close do 2 atoms actually have to be in order to form a chemical bond?
It turns out, getting 2 atoms to form a bond is like trying to get Goldilocks to leave the bears alone. If you put the atoms too close, their positively charged nuclei will go into a panic and start repelling each other. And if you put the atoms too far away, there's basically no attractive forces holding them together.
The graph that conveniently shows us the sweet spot in between is called a potential energy graph. This graph shows us how potential energy changes when atoms are too far apart, too close, and just the right distance from each other to form a bond. When 2 atoms are too close to each other to make a bond, potential energy is really high, since repulsive forces are trying to push the atoms away. When potential energy is at its lowest, in its dip over here, a bond is formed. This extremely low potential energy means that the atoms are in their most stable state, meaning that they formed a bond. And when the atoms are too far apart from each other to bond, their potential energy is zero, since there's no attractive forces between the molecules. The distance over here between the potential energy where the bond is formed to zero is the bond energy, which is the energy required to break the bonds between 1 mole of a covalent molecule. And the shorter the bond, the higher the bond energy. Now let's look at a question that has potential energy graphs. This problem says that this is the potential energy graph for 2 oxygen atoms. First, find the bond length and bond energy. Then, draw the approximate potential energy graph for sulfur. First, we know that the part of the graph with the lowest potential energy is where the oxygen atoms will bond, and that's right about over here. Now, what does this tell us about bond length and bond energy? Let's start with bond length. This part of the graph is the distance between 2 oxygen atoms when they form a bond. So that tells us that the bond length is around 121 picometers, or pm. We also talked about how the distance from zero potential energy to the potential energy of the bond is the bond energy. So that tells us that the bond energy for 2 oxygen atoms is 494 kilojoules per mole of O2. Now we need to draw the potential energy graph for sulfur using this graph. Well, sulfur has 1 more energy level than oxygen, which makes sulfur atoms bigger than oxygen. This means that sulfur atoms will form a longer bond than oxygen, shifting sulfur's graph to the right as internuclear distance increases. Because sulfur has a longer bond, there are less attractive forces between sulfur atoms, giving sulfur atoms less bond energy. That means that the curve for sulfur's bond length will be less deep. So, shifting the curve to the right and making it less steep, sulfur's potential energy graph will look something like this. Well, that's it for today's video. Make sure to subscribe and comment on this video and share it with your friends. Also make sure to ask me any questions in the comments. Thank you all so much for watching. Bye!